So this is what I'm going to be talking about, is how to store a key value store in untrusted cloud server. And this is joint work with my two colleagues, Adam Aviv and Sungol Choi, who are right down here. So I really want to give them some credit for convincing me that there were some interesting problems to work on here, and that's been pretty great. So here's what we're going to do. We want to store, have a key value store, so like a regular map where you give some labels and you can look up the corresponding payload. Everything is going to be stored remotely on a cloud server, and you want to get sort of the maximum amount of privacy where that cloud server that's storing all your data doesn't know anything about what you're storing and also doesn't know anything about the access pattern. So beyond just encrypting the values of what you're storing, you also want to encrypt the correlations between what you're accessing when and things like that. And we also are thinking about some even more powerful attack models other than just obliviousness. So we'll see what that means. Secure deletion and history independence is what we looked at as well. And besides just the security, we want it to be actually usable. And what that means is we want it to be fast. So here's the basic setting. Since there's going to be, I think, like 3 talks at least about ORAMs, so you might as well have a basic idea of what that is. So the principle is that you are storing some kind of a key locally, and you're interacting with a cloud server, and you're assuming that someone is in the middle that's spying on all of your communication and can see everything. And what you're trying to hide is not only the contents of your data, but also the access patterns of what you're accessing. So you can think of it as hiding not just the payloads, but also the metadata. And I think a relevant quote here is from our former NSA director that said, I think last year or 2 years ago, he said, "We kill people based on metadata." So a little bit of a chilling reminder in case you're not convinced that it's worth it to hide access patterns. Somebody said that they kill people based on metadata, so we should maybe think about that. And what we're going to do is address some issues in these existing constructions in our work. And the first problem that we looked at is, what if the size of data is not fixed into fixed size blocks that are all exactly the same? So what if you're storing files? Some of them are a little bit larger, some of them are a little bit smaller. And what can you do about that? Well, what ORAM leaks is the amount of operations that you're performing on an ORAM. So it's oblivious to what the access patterns are, but an attacker can see how much communication you're doing, and from that can say exactly how many operations you did. So if you just break up your large files into some number of blocks, well, now there might be a correlation that can be done between the size of the file, the size of whatever you're doing, and when you did that. And so the first thing we looked at in the first construction we'll see is what we call the VORAM, where the V stands for variable size blocks. And what this allows you to do is to store variable size blocks within an ORAM and still get that obliviousness, so there's not going to be any correlations possible. So the second issue is going beyond just ORAMs. Sometimes you want to store a data structure inside your ORAM, and this was looked at a couple years ago in this great paper at CCS. And the basic idea, as you can see from my excellent picture, is that you have an AVL tree or some kind of other tree that's slapped on top of the ORAM, meaning that each one of the nodes in that data structure is going to be stored in a single block in the ORAM. And then what kind of things happen here? Well, they looked at a lot of these things in this paper and came up with some great ideas. But there's another issue similarly to the different size files, is if you think about an AVL tree, different nodes are at different heights. So if I access some node normally, if it's at height 2, then that should be a little bit of a faster access than accessing something else that's at height 10. But wait, if I allow my data structure to take a different running time depending on what I'm accessing, that's going to break the obliviousness property. So what you have to do is you have to perform dummy operations up to this worst case cost bound. So the second thing we're going to see is a new kind of data structure that's called a herb tree with this long title that we'll actually see what all those parts mean. And it's a fixed height tree data structure. So it's a little bit of a modification of some existing history independent data structures, but the advantage that you're going to get is it's going to work very well within this oblivious setting. All right, the third thing we looked at, if you were at the last talk in the first session this morning, it was looking at multiple attack vectors. And there was this nice picture of someone stealing your cell phone. So what if the spy that's been listening to all of your cloud communication and knows everything that you've ever stored in the server, what if they also coerce your private key? Okay, so this is what we call a catastrophic attack, and it is catastrophic. All of your data is definitely going to be revealed, whatever you're storing, because they have your private key. However, you would still like to get some security here. In particular, whatever you've done in the past that you've deleted from your data structure before your private key gets stolen, you want that to not be able to be accessed by this catastrophic, very powerful attacker. And the only way that we could actually think of that you could do this before our work was to just do the very stupid thing of download the entire database and re-encrypt it and send it back every time. And so we have our VRAM plus Herb. When you put them together, besides this extra performance, we're also going to get these extra security guarantees in the case of a very powerful attacker. Okay, so here's a little bit of outline of what we're going to see. Again, there's these two new things that are really just some not too difficult modifications of prior work. So the VRAM and then the Herb, which will be stored inside the VRAM. So we're going to look at both of those a little bit, how they work, and then you'll see that they actually do work. So here's a little bit more about the VRAM. The general principle is that there's an overhead associated with pathoram. So if you're familiar with the pathoram, then this will make sense to you, and if not, you're going to see an example in a second anyway. That overhead that's associated with each of the operations in a pathoram, we can take advantage of that to be able to store variable size blocks. So what we're going to see is at the top here, so this is a picture of our VRAM. At the top, each one of these blocks is a bucket that's stored on the back end. So everything at the top is actually pieces of information that are stored on the server. And then the actual blocks that you're interacting with are these variable size color blocks at the bottom. And so the server is just storing these fixed size buckets, but within those buckets are variable size blocks. And you can see that the larger ones, like the blue block, is broken up into 3 different parts, which we call chunks. So here's the data structure, and you can see that everything is encrypted with different keys that are, each key is stored in the parent's node. And let's see how this works. So if I'm doing any kind of operation where, let's say I'm looking up this yellow block. So what I'm going to do is look along the path for that block. So you notice that each block is associated with an index. So you're going to look up everything along that path. You're going to read that into your local stash and combine the different pieces, the different chunks of the blocks that you find. So we'll get in our stash, we'll get the entirety of that yellow block, and we'll also get part of the purple block, but not the other parts. But that doesn't matter because we're only looking up the yellow thing. Now what you'll notice, if you think it's a mistake in my slides, it's not. So the number has changed. So the number has changed from 1 to index 6. That's where you get the obliviousness from. And this is all from pathoram, except for the variable size part. So I don't want you to think that I came up with all this. So the index changes, that's what provides obliviousness, so it's going to be randomly reassigned to a different path the next time. And then you write everything back according to the new rules, according to those new paths. And one of the things that I want you to notice in this diagram is that the keys changed along that path. So this is actually the secure deletion part, that when we write something back, we change all of the keys along the path to that original thing that we read. So a little bit more details of what we get out of this. Again, the identifiers are chosen randomly, and that's what provides the obliviousness, but we'll also see it's a little bit of an issue. This is a pretty efficient construction in that you can achieve only 2 rounds of communication for every operation. So all the buckets along the path that you're reading, they can be fetched in parallel because you know exactly the path that you're going to be reading, and then they can be written back in parallel as well. So that can be very fast. And the secure deletion part comes in that since I'm rekeying the entire path every time, including the root node, what that means is that any prior states of the tree aren't recoverable by anyone, including by the original user, because you throw away that old encryption key. And so that's what's going to provide secure deletion in the VRAM context. Okay, now a big question in any ORAM construction is how big do the buckets have to be? So what's the overhead, what's the kind of wastage that we have? And for our VRAM, what we have is roughly a 20 times blow up, which is not great. But this is under this restriction that I want you to remember, that the size of the variable size things that we're storing, they can vary, but they can't vary that much. So the tail of the distribution of whatever the sizes of things that you're storing needs to be a pretty light tail. It needs to be a geometric distribution. So they can vary, but they can't vary hugely, or else you'll lose your efficiency. And if the 20 seems really bad to you, it is, because in fact it's only 6. All right. The next thing I want to talk about is the herb tree. So this is the new data structure that we're going to be storing inside our VORAM. And just a little bit of a motivation, we have these indexes in the VORAM, but they don't mean anything, and they're also changing every time. So you have kind of a chicken and the egg problem of, okay, you have this awesome data structure, how do you remember the indexes of everything? The standard solution is you store a position map in recursively smaller ORAMs, which is one of these beautiful theoretic constructions that I think sounds nice. And then if you go to try to make that work, you're like, it's not great. And the authors of the Oblivious data structures paper actually came up with a great observation, which is that if you're storing a data structure inside here, you don't have to worry about the position map, because you only really need the identifier of the root node, which you can save locally, and then store the subsequent identifiers inside their parent nodes. And so we're going to take advantage of that improvement. But we're not going to use an AVL tree. And so here's a little bit of why. So it's a little bit of an exercise for you in case you came in late. What's the difference between these two AVL trees? So I have two AVL trees here. They're both storing the same 4 items. They're both in order. They're both valid AVL trees. But imagine this is your browsing history, and you had a private browsing tab open, and then you closed it real quick. So you just deleted something from this tree. And I know that you were either browsing Reddit or you were browsing YouTube, but you just deleted it, so it's not in the tree anymore. However, hopefully in this time, you've been able to think about which tree you see, which structure of the tree actually reveals which one of those things was just deleted. So you know from the structure of the tree, from the 4 things that are there, which one of the things was just prior to that removed from it, even though its contents were actually gone from the tree. So this is the security issue that we're going to solve with our herb tree. So it's based on some work on history-independent data structures. What it actually achieves is a notion called strong history independence. What that means is that the state of our data structure depends and is uniquely determined by the contents of whatever's stored in it. So we can't have the situation like we just saw with an AVL tree, where the same 4 items could come in 2 different configurations, which then potentially leak some information. And so that's what strong history independence is. And the way that we actually make this happen is when you create your tree, you randomly choose a hash function from a family of hash functions, and then you're going to use that hash function every time you're inserting something to determine the position, the exact place in that tree where your data belongs, and not just the lateral position, but also the height. So normally in B trees, you would choose the height according to the sequence of operations. If you've taught a data structures class, at some point you're going to split the node and merging nodes and all those wonderful things. We're not going to do things in that way because that would not be history independent. So here's an example. And for the oversimplification here, I'm going to say that the height of every node is determined by the number of trailing zeros in the hash. So what you see in this tree is just a bunch of hashes. You don't know what I'm storing because I'm only going to store the hashes of the keys. All I need to do is look things up, so I don't need to have the original key that the hash came from. And then you can see that like 400 is at the root level because that ends with 2 trailing zeros. And what you should notice right away is that it's different than a regular B tree in that the sizes of the nodes are not going to be in as tight a range as they would be in a normal B tree. So for example, we have one of our leaf nodes is empty. It has nothing inside it, which normally would not ever be allowed to happen in a B tree, but here it has to happen just because with these data items, hopefully you can convince yourself that following the rules of they have to be in order according to the hash, and they have to be on the level according to the number of trailing zeros, we couldn't have it any other way. We can't avoid having that empty node. And so if you want to insert something new, you hash it. If we hashed hello in my totally made up hash function, that ends up with 510. So that's going to end up at the 2nd level. And I know exactly where it's going to go. It couldn't possibly go anywhere else. And so we end up splitting that node, and that's what we see. OK, so we have some similar performance properties to a B tree, but a big difference in that the nodes can vary in their size. And choosing the heights of every element is really crucial to making this whole thing work. And my description of saying the number of trailing zeros is actually not too far off from the probability distribution that we want. So what we do, in fact, is you, as a user, you're allowed to choose an expected block size, which is going to be optimized according to however you're storing it. And then you're going to, every time you insert something new, you'll use its hash to seed a pseudo-random number generator, making it not at all random. And then you'll sample from that random number generator according to a geometric distribution, and that's going to determine the height. So it's similar sort of to how you determine the height of an element in a skip list, actually, but with a biased probability according to how big you want your nodes to be. Cool. So what you should notice is that Herb and VORAM work perfectly together, almost like we specifically designed them only to work in this one context with each other. And that's great, and we're going to see some nice performance benefits from this, and these are some of the aspects. So everything is only stored in the parent nodes, including identifiers in the Herb, and in the VORAM, remember, we're storing encryption keys in each of the parent nodes that also gives us our secure deletion. One interesting thing about that is that when you're thinking about composing these different protocols, so we're thinking about composing a data structure inside an ORAM, the amount of, say, history independence or secure deletion you get is really dependent on both of those pieces. So if you store a perfectly history independent data structure inside a not history independent ORAM construction, then you lose it. And so you really have to have it in both places. Okay. I want to say that we compared to these other things, and what we observed, as you can imagine, is that ours has pretty good performance. You can get better performance for sure than our VORAM plus Herb construction, but to do it, you have to give up a lot of security. So in the four-way comparison here between what we did, the prior work on Oblivious data structures, the prior work on just secure deletion, and this naive baseline, what we saw, and I'll skip back as to why we see this, what we see is that our construction is almost the fastest. It's a little bit not as fast as just doing secure deletion in a B tree, and we shouldn't expect that it would be, because that's really just not providing any obliviousness at all and revealing the access patterns completely. But we get almost as good performance of that, and significantly improved, this is a log scale graph, significantly improved performance compared to the previous Oblivious data structure work. And what I really want to emphasize is look at the y-axis here. We're less than 1 second. So this is measuring one access, the cost of doing one lookup or store or any operation using an actual networked implementation with the server being Amazon Web Services, free tier, and it totally works. And I think you can argue that this is a reasonable performance. If you're willing to wait 1 second, you can use this. So the takeaways, and thank you for your time, are that ORAMs, I think there's an idea that obliviousness would be nice, but it sucks in terms of performance. I think that it doesn't, and I think that it doesn't have to. And we can also get more flexibility in terms of like variable size blocks, and more security in terms of things like secure deletion. So that's it for me. Thanks a lot. I hope there's a couple questions, and thanks again to my co-authors.
Hi, great. Thanks, great talk. So one of the other big downsides of ORAM is single userness, right? So what can you do about that, maybe?
Yeah, nothing. So I'll admit that we can do nothing about that right now, but it's a thought that hasn't not crossed our mind. But I should also say there are some approaches that people are looking at for multi-user ORAMs, and they should compose nicely with what we're doing. So I'm not aware of anything that we're doing that would prevent some of those techniques from being used.
Great.
So it's possible I just missed some point here, but you seem to have some parameterizations that are heuristic and ad hoc, the block size and number of zeros and things.
Okay, so the number of zeros was just for that example. In fact, what you'll do is you'll be seeding this pseudo-random number generator based on the hash, and where you define the distribution. So that's not ad hoc. And the other thing is the block size that you mentioned. So what we did is we proved that you need at most a 20 times factor blow up in your block size. And then what we saw is experimentally, based on the experiments we ran, that can be as low as 6. So if you don't believe in our experiments, then you can stick with the 20 times block size. And if you want to try, then you can go down to 6 is what we found experimentally. And that's similar to other ORAM constructions where there's a little bit of gap, in the constants of your proof.
Well, I'd wondered if you'd taken an oblique look at it through information theory and if you had some notion of number of bits leaked per.
I think the number of bits leaked for any operation should be 0, is what we're trying to. So everything that I've said is with absolutely 0 amount of leakage. And I'm not sure if I don't think the leakage would be elegant once things started to blow up.
So the block size is only for performance, not for security.
So, yeah, so having a larger block size will decrease the probability that you sort of run out of room in a path. And the way that you lose security is that if you run out of room, then the attacker might realize that you've run out of room because you start crying about it or something, and that will leak the fact that you were doing a lot of a certain kind of operation. So that's kind of where that comes in.